Hello everybody. So in today's video we'll be doing the audiobook of NCERT Class 12 Physics textbook Chapter 5 Magnetism and Matter. So let me remind you, if you have not yet subscribed the channel, please do subscribe and please give it a thumbs up, because this is the first time on YouTube that you're getting one shot lectures for audiobooks of Class 12 Physics. So I would strongly suggest you to keep your NCERT book in front of you while I read, so that would be much better. So, Chapter 5 Magnetism and Matter 5.1 Introduction. Magnetic phenomena are universal in nature. Vast distant galaxies, the tiny invisible atoms, humans and beasts, all are permeated through and through with a host of magnetic fields from a variety of sources. The Earth's magnetism predates human evolution. The word magnet is derived from the name of an island in Greece called Magnesia, where magnetic ore deposits were found as early as 600 BC. Complained that their wooden shoes, which had nails at times, stayed. In the previous chapter, we have learnt that moving charges or electric currents produce magnetic fields. This discovery, which was made in the early part of the 19th century, is credited to Ørsted, Ampere, Biot and Savart, among others. In the present chapter, we take a look at magnetism as a subject in its own right. Some of the commonly known ideas regarding magnetism are: 1. The Earth behaves as a magnet with a magnetic field pointing approximately from geographic south to north. 2. When a bar magnet is freely suspended, it points the north-south direction. The tip which points to the geographic north is called the North Pole, and the tip which points to the geographic south is called the South Pole of the magnet. 3. There is a repulsive force when North Pole or South Poles of two magnets are brought close to each other. Conversely, there is an attractive force between the North Pole of the one magnet and the South Pole of the other. 4. We cannot isolate the North or South Pole of a magnet. If a bar magnet is broken into two halves, we get two similar bar magnets with somewhat weaker properties. Unlike electric charges, isolated magnetic north and south poles, known as magnetic monopoles, do not exist. It is possible to make magnets out of iron and its alloys. We begin with a description of bar magnet and its behavior in an external magnetic field. We describe Gauss's law of magnetism. We then follow it up with an account of the Earth's magnetic field. We next describe how materials can be classified on the basis of their magnetic properties. We describe paramagnetic, diamagnetic, and ferromagnetism. We conclude with a section on electromagnets and permanent magnets. 5.2 The bar magnet. One of the earliest childhood memories of the famous physicist Albert Einstein was that of a magnet gifted to him by a relative. Einstein was fascinated and played endlessly with it. He wondered how the magnet could affect objects such as nails or pins placed away from it and not in any way connected to it by a spring or string. We begin our study by examining iron filings sprinkled on a sheet of glass placed over a short bar magnet. The arrangement of iron filings is shown in figure 5.1. The pattern of iron filings suggests that the magnet has two poles similar to the positive and negative charge of an electric dipole. As mentioned in the introductory section, one pole is designated the North Pole and the other the South Pole. When suspended freely, these poles point approximately towards the geographic north and south poles, respectively. A similar pattern of iron filings is observed around a current-carrying solenoid. 5.2.1 The magnetic field lines. The pattern of iron filings permits us to plot the magnetic field lines. This is shown both for the bar magnet and the current carrying solenoid in figure 5.2. For comparison, refer to chapter 1, figure 1.17d. Electric field lines of an electric dipole are also displayed in figure 5.2c. The magnetic field lines are visual and intuitive realization of magnetic field. Their properties are 1. Magnetic field lines of a magnet or a solenoid form continuous closed loops. This is unlike the electric dipole where these field lines begin from a positive charge and end on the negative charge or escape to infinity. 2. The tangent to the field line at a given point represents the direction of the net magnetic field B at that point. 3. The larger the number of the field lines crossing per unit area, the stronger is the magnitude of the magnetic field B. In figure 5.2a, B is larger around the region 2 than around region 1. The magnetic field lines do not intersect, for if they did, the direction of the magnetic field would not be unique at the point of intersection. So one can plot the magnetic field lines in a variety of ways. One way is to place a small magnetic compass needle at various positions and note its orientation. This gives us an idea of the magnetic field direction at various points in space. 5.2.2 Bar magnet as an equivalent solenoid. In the previous chapter, we have explained how a current loop acts as a magnetic dipole. We mentioned Ampere's hypothesis that all magnetic phenomena can be explained in terms of circulating currents. The resemblance of magnetic field lines for a bar magnet and a solenoid suggests that a bar magnet may be thought of as a large number of circulating currents in analogy with a solenoid. Cutting a bar magnet in half is like cutting a solenoid. We get two smaller solenoids with weaker magnetic properties. The field lines remain continuous, emerging from the one face of the solenoid and entering into other phase. One can test this analogy by moving a small compass needle in the neighborhood of a bar magnet and a current carrying finite solenoid and noting that the deflections of the needle are similar in both cases. To make this analogy more firm, we calculate the axial field of finite solenoid depicted in figure 5.3. We shall demonstrate that at large distances this axial field resembles that of a bar magnet. So B is equal to mu 0 divided by 4 pi into 2m divided by r cube. This is also the far axial magnetic field of a bar magnet, which one may obtain experimentally. Thus, a bar magnet and a solenoid produce similar magnetic fields. The magnetic moment of a bar magnet is thus equal to the magnetic moment of an equivalent solenoid that produces the same magnetic field. 5.2.3 The dipole in a uniform magnetic field. Let's place a small compass needle of known magnetic moment m and allowing it to oscillate in the magnetic field. This arrangement is shown in figure 5.3b. The torque on the needle is C. See equation 4.29. Tau is equal to m cross b. In magnitude, tau is equal to mb sin theta. Here tau is restoring torque and theta is the angle between m and b. An expression for magnetic potential energy can also be obtained on lines similar to electrostatic potential energy. The magnetic potential energy um is given by um is equal to integral tau theta into d theta is equal to integral mb sin theta d theta is equal to minus mb cos theta. Therefore, um is equal to minus m dot b. We have emphasized in chapter 2 that zero of potential energy can be fixed at one's convenience. Taking the constant of integration to be 0 means fixing the zero of potential energy at theta is equal to 90 degree. That is, when the needle is perpendicular to the field, equation 5.6 shows that potential energy is minimum equal to minus mb at theta is equal to 0 degree, which is the most stable position, and maximum is equal to plus mb at theta is equal to 180, most unstable position. 5.2.4 The electrostatic analog. Comparison of equation 5.2, 5.3 and 5.6 with the corresponding equations for electric dipole of chapter 1 suggests that magnetic field at large distances due to bar magnet of magnetic moment m can be obtained from the equation for electric field due to an electric dipole of dipole moment p by making the following replacements. Like we replace E with B, P with M, and 1 by 4 pi epsilon 0 with mu 0 divided by 4 pi. In particular, we can write down the equatorial field BE of a bar magnet at a distance r for r very much greater than L, where L is the size of the magnet. Therefore, B equatorial is equal to minus mu 0 by 4 pi into m by r cube. Likewise, the axial field BA of a bar magnet for r very much greater than L is B axial is equal to mu 0 by 4 pi into 2m divided by r cube. Equation 5.8 is just equation 5.2 in the vector form. Table 5.1 summarizes the analogy between electric and magnetic dipoles. Table 5.1 The dipole analogy. Permittivity and permeability. Electrostatics, we have 1 by epsilon 0. In magnetism, we have mu 0. Dipole moment. Electrostatics P, magnetism M. Equatorial field for a short dipole. Electrostatics minus P by 4 pi epsilon 0 r cube. Magnetism minus mu 0 m by 4 pi r cube. Axial field for a short dipole 2p by 4 pi epsilon 0 r cube in electrostatic, and in magnetism we have mu 0 into 2 pi 2m divided by 4 pi r cube. External field, that is torque. In electrostatics we have p cross E, magnetism we have m cross B. Energy, in electrostatics we have minus p dot E, magnetism minus m dot B. 5.3 Magnetism and Gauss's law. In chapter 1 we studied Gauss' law of electrostatics. In figure 5.3c we see that for a closed surface represented by 1, the number of lines leaving the surface is equal to the number of lines entering it. This is consistent with the fact that no net charge is enclosed by the surface. However, in same figure for the closed surface 2, there is a net outward flux since it does include a net positive charge. The situation is readily different for magnetic fields which are continuous and form closed loops. Examine that Gauss's surface represented by 1 or 2 in figure 5.3a or 5.3b. Both cases visually demonstrate that the number of magnetic field lines leaving the surface is balanced by the number of lines entering it. The net magnetic flux is 0 for both the surfaces. This is true for any closed surface. Refer figure 5.5, where you can see an n vector. It's a unit vector, and you can see a b vector and an area delta s and theta between them. Consider a small vector area element delta s of a closed surface S as in figure 5.5. The magnetic flux through AS is defined as delta 5B is equal to B dot delta S, where B is the field at delta S. We divide S into many small area elements and calculate the individual flux through it. Then the flux phi b is phi b is equal to summation all delta phi b is equal to summation all b dot delta s is equal to 0, where all stands for all area element delta S. Compare this with the Gauss's law of electrostatics. The flux through closed surface in that case is given by phi E is equal to sigma E dot delta S is equal to Q by epsilon 0, where Q is the electric charge enclosed by the surface. The difference between the Gauss's law of magnetism and that for electrostatics is a reflection of the fact that isolated magnetic poles, also called monopoles, are not known to exist. There are no sources or sinks of B. The simplest magnetic element is a dipole or a current loop. All magnetic phenomena can be explained in terms of arrangement of dipoles or current loops. Thus, Gauss's law for magnetism is that the net magnetic flux through any closed surface is 0. Magnetization and magnetic intensity 5.4. The earth abounds with a bewildering variety of elements and compounds. In addition, we have been synthesizing new alloys, compounds, and even elements. One would like to classify the magnetic properties of these substances. In the present section, we define and explain certain terms which will help us to carry out this exercise. We have seen that a circulating electron in an atom has a magnetic moment. In a bulk material, these moments add up vectorally and they can give a net magnetic moment which is non-zero. We define magnetization capital M of a sample to be equal to its net magnetic moment per unit volume. Capital M magnetization is equal to M net divided by V, or net magnetic moment per unit volume. M is a vector with the dimensions L raised to minus 1 A and is measured in units of AM raised to minus 1. Consider a long solenoid of n turns per unit length and carrying a current I. The magnetic field in the interior of the solenoid was shown to be given as B0 is equal to mu 0 Ni. If the interior of the solenoid is filled with a material with non-zero magnetization, the field inside the solenoid will be greater than B0. The net magnetic field in the interior of the solenoid may be expressed as B is equal to B0 plus Bm, where B0 is that of solenoid and Bm is that of material. It turns out that this additional field Bm is proportional to the magnetization M of the material and is expressed as Bm is equal to mu 0 into M, where mu 0 is the same constant, that is permittivity of vacuum, that appears in Biot-Savart's law. It is convenient to introduce another factor, field H, called the magnetic intensity, which is defined by H is equal to B divided by mu 0 minus M. H has the same dimensions as M, that is L raised to minus 1 A, and is measured in units of ampere meter inverse. Thus, the total magnetic field B is written as B is equal to mu 0 into H plus M. We repeat our defining procedure. We have partitioned the contribution to the total magnetic field inside the sample into two parts. One, due to external factors such as the current in the solenoid. This is represented by capital H. The other is due to the specific nature of the magnetic material, namely capital M, that is magnetization, and the latter quantity can be influenced by external factors. This influence is mathematically expressed as M is equal to chi H, where chi, a dimensionless quantity, is appropriately called magnetic susceptibility. It is a measure of how a magnetic material responds to an external field. Table 5.2 lists chi for some elements. It is small and positive for materials which are called paramagnetic. It is small and negative for materials which are diamagnetic. In the latter case, M and H are opposite in direction. From equations 5.16 and 5.17 we obtain that B is equal to mu 0 into 1 plus H in 1 plus chi into H is equal to mu 0 into mu R into H is equal to mu H. I repeat, B is equal to mu 0 into 1 plus chi into H is equal to mu 0 into mu R into H. Therefore, B is equal to mu H, where mu R is equal to 1 plus chi is a dimensionless quantity called the relative magnetic permeability of the substance. It is the analog of the dielectric constant in electrostatics. The magnetic susceptibility of the substance is mu, and it has the same dimensions and units as mu 0. So, mu is equal to mu 0 mu R is equal to mu 0 into 1 plus chi. The three quantities chi, mu R and mu are interrelated and only one of them is independent. Given one, the other two may be easily determined. 5.5 Magnetic properties of materials. The discussion in the previous session helps us to classify materials as diamagnetic, paramagnetic or ferromagnetic. In terms of the susceptibility chi, a material is diamagnetic if chi is negative, para if chi is positive and small, and ferro if chi is large and positive. A glance at table 5.5 gives one a better feeling for these materials. Here, epsilon is a small positive number introduced to quantify paramagnetic materials. Next, we describe these materials in some detail. Table 5.3 Diamagnetic, paramagnetic, ferromagnetic. Diamagnetic, chi between -1 and 0. -1 less than or equal to chi less than 0. 0 less than or equal to mu R less than 1. Mu less than mu 0. For paramagnetic, 0 less than chi less than epsilon. 1 less than mu R less than 1 plus epsilon. Mu greater than mu 0. Ferromagnetic, chi very much greater than 1. Mu R very much greater than 1. And mu very much greater than mu 0. Diamagnetism. Diamagnetic substances are those which have tendency to move from stronger to the weaker part of external magnetic field. In other words, unlike the way a magnet attracts metals like iron, it would repel a diamagnetic substance. Figure 5.7a shows a bar of diamagnetic material placed in an external magnetic field. The field lines are repelled or expelled and the field inside the material is reduced. In most cases, this reduction is slight, being 1 part in 10 raised to 5. When placed in non-uniform magnetic field, the bar will tend to move from high to low field. The simplest explanation for diamagnetism is as follows. Electron in an atom orbiting around the nucleus possess orbital angular momentum. These orbiting electrons are equivalent to current carrying loop and thus possess orbital magnetic momentum. Diamagnetic substances are the ones in which resultant magnetic moment in an atom is 0. When diamagnetic field is applied, those electrons having orbital magnetic moment in the same direction slow down and those in the opposite direction speed up. This happens due to induced current in accordance with the Lenz's law, which you will study in chapter 6. Thus, the substance develops a net magnetic moment in direction opposite to that of the applied field and hence repulsion. Some diamagnetic materials are bismuth, copper, lead, silicon, nitrogen at STP, water and sodium chloride. Diamagnetism is present in all the substances. However, the effect is so weak in most cases that it gets shifted by other effects like paramagnetism, ferromagnetism, etc. The most exotic diamagnetic material are superconductors. These are metals cooled to very low temperatures which exhibit both perfect conductivity and perfect diamagnetism. Here, the field lines are completely expelled. Chi is equal to -1 and mu r is equal to 0. A superconductor repels a magnet and by Newton's third law is repelled by the magnet. The phenomenon of perfect diamagnetism in superconductors is called Meissner effect, after the name of its discoverer. Superconducting materials can be gainfully exploited in variety of situations. For example, for running magnetically levitated superfast trains. 5.5.2 Paramagnetism. Paramagnetic substances are those which get weakly magnetized when placed in an external magnetic field. They have tendency to move from a region of weak magnetic field to strong magnetic field. That is, they get weakly attracted to a magnet. The individual atoms or ions or molecules of a paramagnetic material possess permanent magnetic dipole moment of their own. On account of the ceaseless random thermal motion of the atoms, no net magnetization is seen. In the presence of an external field B0 which is strong enough, at low temperatures the individual atomic dipole moment can be made to align and point the same direction as B0. This figure 5.7 shows a bar of paramagnetic material placed in an external field. Field lines gets concentrated inside the material and field lines is enhanced. In most cases, this enhancement is slight, being 1 part in 10 raised to 5 when placed in a non-uniform magnetic field. The bar will tend to move from weak field to strong. Some paramagnetic materials are aluminium, sodium, calcium, oxygen at STP, and copper chloride. For paramagnetic material, both chi and mu r depend not only on the material but also on the sample temperature. As the field is increased or the temperature is lowered, magnetization increases until it reaches the saturation value, at which point all the dipoles are perfectly aligned with the field. 5.5.3 Ferromagnetism. Ferromagnetic substances are those which get strongly magnetized when placed in an external magnetic field. They have strong tendency to move from a region of weak magnetic field to strong magnetic field. That is, they get strongly attracted to a magnet. The individual atoms or ions or molecules in a ferromagnetic material possess a dipole moment as in paramagnetic material. However, they interact with one another in such a way that they spontaneously align themselves in a common direction over a macroscopic volume called a domain. The explanation of this cooperative effect requires quantum mechanics and is beyond the scope of this textbook. Each domain has a net magnetization. Typical domain size is 1 millimeter and domain contains about 10 raised to 11 atoms. The first instant, the magnetization varies randomly from domain to domain and there is no bulk magnetization. This is shown in figure 5.8a. When we apply an external magnetic field B0, the domains orient themselves in the direction of B0 and simultaneously the domain oriented in the direction of B0 grow in size. This existence of domains and their motion are not speculations. One may observe this under a microscope after sprinkling a liquid suspension of powdered ferromagnetic substance of samples. This motion of suspension can be observed. Figure 5.8b shows the situation when domain have aligned and amalgamated to form a single giant domain. Thus, in a ferromagnetic material, field lines are highly concentrated. In non-uniform magnetic field, the sample tends to move towards the region of high field. We may wonder as to what happens when the external field is removed. In some ferromagnetic materials, the magnetization persists. Such materials are called hard magnetic materials or hard ferromagnets. Alnico, an alloy of iron, aluminium, nickel, cobalt, and copper is one such material. The naturally occurring iodostone is another. Such materials form permanent magnets to be used among other things as a compass needle. On the other hand, there is a class of ferromagnetic materials in which magnetization disappears on removal of external field. Soft iron is one such material. Appropriately enough, such materials are called soft ferromagnetic materials. There are number of elements which are ferromagnetic like iron, cobalt, nickel, gadolinium, etc. The relative magnetic permeability is greater than 1000. The ferromagnetic property depends on temperature. At high enough temperature, ferromagnetic becomes paramagnetic. The domain structure disintegrates with temperature. This disappearance of magnetization with the temperature is gradual. Thank you. So this is all for this whole chapter. If you like this, please subscribe the channel and like the video for more updates. So please comment down your heartfelt comments and I will make necessary arrangements to improve my content. So thanks for watching. Bye bye.